Hello, and welcome to today's Aviation Week webinar, Mitigating Risk, Highly Reliable Alternatives to Pyrovalves, sponsored by the Lee Company. I'm Mike McClary, and I'll be moderating today's event. We have just a few housekeeping announcements before we begin. The first is that we've designed this webinar to be interactive. The remote control of widgets to the right of your screen will allow you to learn about today's speaker and to participate in the Q&A session. Next, the slides will advance automatically throughout the event. If at any time you experience difficulties with the audio or playback of the presentation, simply refresh your browser. This typically fixes any issues. If the browser refresh doesn't solve your technical problem, just type your issue into the Q&A area and we'll offer one-on-one assistance. Finally, toward the end of our webinar, you'll see a window pop up with our event survey. Please take a minute to fill this out before leaving us today because your feedback provides valuable information on how we can improve future webinars. Now, on to the presentation, Mitigating Risk, Highly Reliable Alternatives to Pyrovalves. Discussing today's topic is Brendan Netkoff. Brendan is Business Development Manager for Aerospace and Energy with the Lee Company. To learn more about Brendan, you can check out his bio in the information widget found within the remote control. That takes care of all the housekeeping. Let's get started. Brendan, take it away.
Thanks, Mike. Appreciate the introduction and welcome everyone. Thank you for joining today's webinar where we'll be discussing mitigating risk. And we're going to take a look at some highly reliable alternatives to pyrovalves. So around the globe, we're seeing a lot of changes and advancements in the aerospace and defense industries. And with that, there's a clear demand for components that are safer, reusable, and easier to qualify. So for the next 15 minutes or so, we're going to explore why aerospace and defense programs are moving away from pyrotechnic valves. We're going to look at what some smarter alternatives look like. We'll go over a few things you can expect from making the switch. And then finally, I'll leave 15 minutes or so to answer some questions that you guys might have. So pyrovalves have been around for many years, but there's several reasons you might consider replacing them with an alternative solution. First of all, traditional pyrovalves can introduce a significant amount of risk. Things like high shock loads, debris generation or foreign object debris, also known as FOD, or electromagnetic interference or EMI sensitivity can all be some major problems with pyrovalves. Additionally, these are single-use components. That means that testing and qualification can become very expensive since each test destroys the hardware and it requires you to then replace it. And as defense and aerospace platforms are evolving, programs are demanding reusable, testable, and lower maintenance components that reduce lifecycle complexity and cost. So by replacing pyrovalves with a modern alternative, you can better align with some modern requirements that are being driven by the market. So starting off, let's take a look at what a pyrovalve is and where these are typically used. Pyrovalves are pyrotechnic devices that isolate and control fluids and are one-time use components. When an electrical signal is sent to the valve, it triggers the igniter or the squib. This starts an explosive chemical reaction within the pyrotechnic cartridge, which generates a high-pressure gas. That high-pressure gas can then be used to push a piston, which can open a sealed passage or close a sealed passage, or it can push a cutter, which can shear a diaphragm or a foil seal. Some common places that you'll see these valves used would include things like a weapons ejection system on a military aircraft. In this case, the high-pressure gas that's generated by the pyrovalve can be used to push directly on a piston, which forces a missile or a bomb out and away from the aircraft safely, even at high speeds. We also see pyrovalves commonly used in the missile as well. Here, they act as an isolation valve in the fuel system so that while the missiles remain unused, the fuel is isolated in the fuel tank for longer periods. But then once the missile is fired, that pyrovalve is activated to open up the flow path from the fuel tank to the combustor. And then one more place we see these commonly used would be spacecraft propulsion systems. Here they can be used to open up the propellant or the pressurization system used to pressurize the propellant. Similar to a missile fuel system, they're just isolating that fuel or fluid from something downstream. So basically, pyrovalves are used anywhere you need a sealing device with rapid actuation. So let's take a quick look at some of the challenges that you might want to consider when you are designing in a pyrovalve or an alternative device. So I've mentioned pyrovalves are single-use components. They cannot be retested or reused, which poses a particular challenge when you're trying to validate, qualify, or accept production hardware into your system. As I mentioned, the individual valves can't be tested to ensure it was properly manufactured. This means that the best you can do is do a lot test on your production lot. So for instance, NASA mandates that at least 10% or 10 units of every manufactured lot have to be tested, and that results in destroying what could be good hardware. And you're doing this just to verify the reliability of the remaining flight hardware. In addition to that, pyrovalves pose some operational risks to the system where they're installed. They are known to create high shock loads. These are explosive devices and can create shock of over 200,000 Gs to their surrounding system architecture. So that means that designers need to carefully assess the structure that's supporting the valves to make sure that it can withstand these high loads from the pyro shock. Additionally, byproducts of the explosive charge would include things like explosive gases, which can be a problem for certain satellite applications. Also, there's a shearing material in some of these where the foil seal is either punctured or sheared, and that can create foreign object debris or FOD, which can get into the fluid path and potentially contaminate some of the components downstream, leading to a premature failure of those components. Lastly, most pyrovalves use a thin bridge wire, which if a stray current caused by electromagnetic interference, if that gets into that bridge wire, it could cause that bridge wire to overheat and cause the pyrovalve to fire unintentionally. Another important thing to look at are the safety and logistics around pyrovalves. Again, these are classified as hazardous explosive materials. There are a lot of strict regulations for obtaining these parts, transporting them, discarding the materials. Additionally, once the parts are on site, they need to have a special location for storage, and certified ordnance personnel are required to be handling these components to make sure that they're properly handled safely. And finally, all of this really adds up to a high cost of ownership. There's a financial burden associated with everything that I've mentioned: the single use, the operational risks, the safety and logistics. So then once you factor in the potential for these valves might need to have redundancy or customization added to it, it's easy to see how these costs can escalate quite quickly. So luckily, there are some alternative options out there. So I'll go over a few of these. I've kind of broken these up into two general buckets: passive actuation and non-passive actuation. So passive solutions would be those that are triggered by things like a change in pressure or temperature. And that would include components like burst elements or mechanical valves. There's no electrical input with these passive solutions, which makes them better suited for EMI sensitive applications. And these are most commonly used in situations where they're used to isolate a fluid for a long time, typically at a lower pressure condition. Non-passive valve solutions, that might include things that require an electrical signal to actively control that component, and would include things like a solenoid valve, where an electromagnetic force is used to quickly alter the state of the valve, or a shape memory alloy actuator, or SMA. Here, an electric current is used to heat up a metal wire And when that happens, it can generate a motion to open or close a valve. The SMAs are a bit slower, but they do provide a high power density. And then lastly, we've added in here pneumatically actuated options. So as some industries are moving toward pneumatic actuation systems on larger platforms, like missile ejection systems on a fighter aircraft, here they use a built-in compressor that charges an accumulator, and that provides a pressure source, eliminating the need for a pyrotechnic device. So let's take a quick look at a couple of these options that the lead company can offer. So when a changing pressure condition can actuate a device, this is where a passive solution can be used. An example of this might be something like a turbojet engine in a missile, where fuel is stored for long periods of time at ambient temperatures and pressures. An isolation device is typically needed in the fuel line to ensure that that fuel cannot migrate from the fuel tank out to the engine. But then once that fuel is turned on, fluid pressure is going to build up in the supply line and then can be used to force open that isolation device. So for applications like these, the lead company offers a zero leak latching mechanical valve, which is what I have shown here. So let's just talk quickly about how this works. In this design, a poppet is seated up against a elastomeric seal, and that prevents any leakage past the valve during storage. There's a detent feature that holds that poppet up against the seat and keeps it positively positioned there to make sure that the valve stays closed. But then once pressure and flow are increased in the system, the valve poppet will shuttle and latch into the open position. And then it'll stay in that position regardless of how much flow or pressure is being supplied by the pump. So with this design, it's purely mechanical. There's no electrical input required, which completely removes any concern for EMI. The valve has no shearing material or explosive compounds, which eliminates risks of foreign object debris or contamination getting downstream. The valve is bistable, which means it can remain in either position without any system inputs, and it's fully resettable so that it can support multiple actuations. So again, this valve is testable. It's something that, and it's retestable, something that Pyrovalves cannot do. The valve uses a ball and a spring detent feature to keep the valve latched closed or latched open. So with this, we offer latching pressures up to 120 psi-d, and we can meet extremely tight leakage performance down to 1 × 10⁻⁵ SCCS of helium. And we are testing 100% of these valves to make sure that both the latching pressure and the leakage performance meets our requirements before they leave our facility. The valve is extremely lightweight at less than 3 ounces. And this valve is derived from our standard shuttle valve. So we have decades of flight pedigree and thousands of parts in service so that we know that these parts are compatible with typical fuels, gases, and petroleum-based fluids. And lastly, we'll just mention this valve is offered with AS standard porting. So it's very easy to integrate into most of these fuel systems by just threading this in. So if you need a passive EMI immune solution that's reusable and customizable, this would be a great option. The next one I'll talk about would be a non-passive solution. So in some cases, when fluid is stored in a higher pressure condition, you're going to need an active or non-passive solution here. An example of this might be something like a helium pressurant tank on a satellite propulsion system, where a valve is used to isolate the helium from the diaphragm in a propellant tank while the satellite is being launched. This needs to stay closed against both the fluid pressure and the vibrational forces during launch or stage separation. But then once the spacecraft or satellite is ready to initiate the propulsion system, an outside input like an electrical signal can be sent to the valve or the component to open it up. This allows the helium to then flow and pressurize the propellant tank downstream. So for applications like this, the Lee company offers our pneumatic isolation solenoid valve, which we have shown here. With this design, a small amount of electric current is needed to energize the solenoid coil, which moves an armature and opens and closes the valve. So you can see in this cross section here, we've got, you can see some of the components inside to see where that electromagnetic coil is and pulls the armature. This one combines features of our proven hydraulic piloting solenoid valve with a new valve body and polyimide shaft tip that deliver a tighter leakage performance for pneumatic applications. So like the mechanical latching valve, there's no shock, there's no pyrotechnics here. There's no risk of FOD getting downstream when this valve is actuated because there's no puncturing or shearing of materials in this valve. We do offer a latching design as well that has a permanent magnet in the valve coil. So that'll keep the valve in its state, either open or closed in the event that power is removed or if there's a power loss in the system. This valve is pneumatically tested to verify the leak tight sealing throughout its rated pressure range, with leakage as little as 1 × 10⁻⁶ SCCS on helium, and that can be for pressures as high as 8,000 psid. Once again, I'll mention we 100% test all of our valves that we build just to make sure that the performance is meeting all of our specified requirements. And then our customers are also able to run similar testing both at component and assembly levels to make sure that the parts are functioning properly. Again, this valve is very lightweight at just under 3 ounces, similar to the latching mechanical valve. And it's also rated for gases, fuels, and petroleum-based fluids. And then the last thing I'll just mention on this valve, you can see a couple different configurations here. We have, our valve is designed to install into a manifold block, but we do have some adapters available with AS porting or tube stub porting, as well as a face mount adapter if needed. So moving from a pyrotechnic device to a mechanical or solenoid-based solution can be really straightforward, but you want to follow the right plan. So there's a few things that you should expect when you're making that switch. First of all, expect a partial redesign. You might need to update things like fittings, manifolds, or control wiring to adapt to the alternative solution. In many cases, designs can be offered that fit existing envelopes, but it may come with a few trade-offs to things like weight or complexity. It's best to start with component level testing before you fully integrate these components into assembly. So that's where the Lee company's solutions are particularly well suited, since they can be reused and retested over and over again. So we'll suggest that you bench test all of our parts to confirm things like latching conditions or verify leakage performance or response time under different temperatures and pressure profiles. And then when you are making the switch to a Lee company device, you can expect to use us as an extension of your engineering team. We offer full support throughout the modeling, the diagnostics process, and the qualification process. We provide guidance to align all of our parts with your application, and we can ensure that a smooth transition from the initial design verification all the way up through your system qualification. So how can Lee Company help? We've been a trusted partner in the aerospace industry for over 75 years. We've spent decades inventing miniature fluid control components. We have a lot of experience to anticipate design challenges before they even arise. We are often recognized by our customers for our exceptional quality and reliability, and we have 22 offices around the globe that are staffed with sales engineers ready to support all of our customers. And with over 1 million square feet of state-of-the-art facilities, we have plenty of manufacturing space to support even the most ambitious projects. So with that, I'd like to just say thank you for your time and attention. I hope this was informative, and I think at this point we can probably open it up to any questions.
All right, great. Thanks, Brendan. Okay, as you said, on to the Q&A. As a reminder, to participate in the Q&A session, just simply click on that Q&A icon, type your question into the text box, and if we are able to get to all the questions, we'll be sure to give them to Brendan so he can reply offline. All right, we've got a bunch here. Brendan, let's jump right in. How do these alternative options compare to a Pyrovalve's size and weight?
Yeah, so our solutions would be comparable to Pyrovalves, if not a little bit smaller and lighter. Both the mechanical latching valve and pneumatic isolation solenoid valve are roughly 3 ounces. And they're pretty similar in size as well, at about 2 inches long and less than 1 inch in diameter. So I would just say that they're pretty comparable, if not a little bit smaller.
All right, let's jump to the next one here. What latching pressures are offered with the mechanical valve?
Yeah, so short answer there would be anywhere from 20 PSID up to 500 PSID. And I'll just kind of elaborate on that a little bit. So the latching mechanical valve uses a detent feature, which is what creates that latching pressure, also combined with the valve seat geometry. So we have the ability to play with those features a little bit to modify that latching pressure. But I will add that the latching pressure should be based on the application where the valve's going to be used. So for instance, in a missile application, you're going to want to make sure that the latching pressure is going to be higher than any pressure that would be generated from something like thermal expansion of that fluid. Additionally, the latching pressure needs to be lower than the maximum output pressure from the pump, just to make sure that that pump can pop the valve open.
Right. We have a couple, and I'm going to summarize these. How do the response times of your solutions differ from Pyrovalves?
Yes, so our response times would be comparable to Pyrovalves as well. Lee Company solenoid valves can be anywhere from generally 10 to 40 milliseconds. When they're operating on pneumatics or gases, that's where you'll see closer to a 10 millisecond response time with our solenoids. And then if it's using something like a cold hydraulic fluid, you'll see response times closer to maybe 40 milliseconds. Our latching mechanical valves are also going to be in that 10 to 40 millisecond range as well. And one thing to add there is that these valves, they do respond quicker when we can pop them open using a higher pressure supplied to delatch that solution.
Got it. Okay. How should I decide between using the passive or non-passive solution?
So with the passive or non-passive decision, that's going to be based on the system where the valves are. Fluid is stored at a high pressure state and has no mechanisms to increase any further. You're going to want to look probably towards a non-passive solution. Additionally, if there's any EMI requirements preventing the use of electromechanical components, that's where you might want to look at something like a passive option.
Got it. Okay. Are there any concerns that the mechanical valve could latch open prematurely?
No. So all of our valves are 100% tested. I know I've said it many times, but it's an important part of our designs. So we are testing the function of our latching mechanical valves before they leave our facility, and we make sure that the latching pressure is within the acceptable range. These valves use a detent feature that has been around since the early 90s. That detent feature was initially designed for our three-way shuttle valves. So we've got a lot of confidence in the performance of that, and we are able to ensure that our latching pressures fall within the specified range before we ship it.
Got it. All right. Let's see here. I've got a bunch of questions. Making sure I'm going. How do you reset the passive valves?
Yeah, that's pretty easy. Basically, you just need to disconnect the outlet port on the mechanical valve. Once you do this, you can access the poppet, the backside of the poppet. So then you just take a simple gauge pin and you can press on the backside of the poppet to push it to the closed position. And then that closing force is something you can typically do by hand. And then once the valve is reset, the outlet port can be reinstalled and the valve is ready to use.
All right, we have a few more minutes here. We'll get a few more questions answered. Do you have a solenoid solution that could support leak-tight operation for storage of nitrogen gas at pressure of 6,000 psig for up to a 10-year duration? Hopefully I got all that right.
Yeah. So our solenoid valves can be rated up to 8,000 psid, operating on a pneumatic application, that's no problem. We have plenty of our zero leak designs offer bubble type performance, or they can be rated for even higher leakage standards, as much as 1 × 10⁻⁶ SCCS on helium. So we can qualify our parts to be rated for long-term high pressure use on a pneumatic system.
All right. How does your solenoid valve integrate into typical fluidic systems?
So the standard Lee Company solenoid valve is offered with what's called a Lee multi-seal. That was developed to replace a traditional O-ring style seal that you would see on other solenoids. The multi-seal is a smaller package. It's the interface needed is easier to produce for our customers, and it eliminates some of the typical concerns that you would have with O-rings pressing through cross-drilled ports, where those O-rings can shear and create FOD downstream. So that multi-seal it's a static seal between all the different ports. But if you do not have a manifold application that can use the multi-seal, we do have other options. As I mentioned, there's adapters with standard AS porting or tube stub porting, and we also have face mount style valves available too.
All right, we have time. Let's squeeze in one more question. What is the rated service life of these valves?
Typically, design intent for our valves is going to be life of an aircraft, but for things like fuel applications, we comply with a 20-year fuel storage life. We always work with our customers to make sure that our parts are going to work well within their applications. We check for things like material compatibility, just to ensure that there's not going to be any issues down the line. And if there is something that we expect, we can always adjust the materials and swap it out for something that will be compatible.
Terrific. All right, we're gonna have to end there. So before we sign off, I'd like to thank our presenter, Brendan, as well as our sponsor, the Lee Company. In the next 24 hours, you'll receive a follow-up email with a link to the on-demand version of today's presentation. Feel free to pass that along to anyone who couldn't join us live today. So again, we want to thank you so much for attending, and we look forward to seeing you again soon on another Aviation Week webinar.